Now you have, for starting this session of engineering technology in Auditorium 2, Miguel Montenegro, that will present the title of his presentation is a Rheological characterization of eco-friendly non-Brownian suspensions. Please, you can start your presentation.
Okay, thank you for the introduction. Good morning, everyone. My name is Miguel Montenegro, and I am currently a PhD student working at the Faculty of Engineering of University of Porto. And in this work, I will be presenting the complete rheological characterization of eco-friendly dense suspensions able to provide shear thickening behavior. The use of fluid in energy dissipating systems is a common strategy to turn unwanted kinetic energy into heat energy, which is dissipated through the fluid itself. Traditionally, the fluid used in these systems has been Newtonian, which provides a linear relationship between stress and strain rates, thus dissipating an amount of energy determined and limited by the viscosity of the fluid, unable to damp external loads in a selective way. However, with shear thickening fluids, which are non-Newtonian, these limitations can be overcome and allow enhanced selectivity either by external field activation or the passive response to critical amplitude and or transient timescales, since the relationship between stress and strain rate is nonlinear. These kinds of systems can be designed to reduce unwanted vibrations, like in the case of viscoelastic liquid dampers, consisting of a moving piston or plate with an open container filled with a viscoelastic liquid, or viscoelastic solid dampers, which can consist in a sandwich structure of steel or cork plates intercalated with layers of a viscoelastic polymer. And another application involving shear thickening fluid in energy dissipating systems can be found in armoring or passive body armor, for example, where the shear thickening fluid is incorporated into the system by impregnating a piece of fabric, increasing its bulletproof resistance. So the objective of the present work consisted of the formulation and rheological characterization of an eco-friendly shear thickening material so that in future works it is possible to predict its behavior when used as a part of a composite material capable of functioning as a damping device. Several concentrated suspensions of precipitated calcium carbonate particles with different morphologies and sizes dispersed in a glycerin carrier fluid with different mass concentrations were prepared and submitted to rotational and extensional rheological tests. For the accomplishment of the task, the selected formulation of the shear thickening fluid had to be set up, so a reference sample was prepared, which formulation was known from previous studies. This sample consisted of a dispersion of PCC in a glycerin carrier fluid with a 55% mass fraction. The PCC particles were supplied by sigma Aldrich and presented a circular aspect ratio as shown in figure 6. It is known from the literature that particles with an aspect ratio of about 4:1 induce shear thickening behavior to the fluid, and the particles used in the reference sample fulfill this requirement. The glycerin was supplied by Lauer spirits, and its properties are reported in table 1. And from the reference sample, successive dilutions were carried out in order to obtain the desired concentrations. Each mixture was mechanical stirred for 2 hours in raw oak and wood, shown in figure 7, and stored in a plastic container sealed with paraffin film, left in a roller mixer in order to facilitate dispersion and prevent sedimentation of the particles. And 3 other suspensions with 55% mass fraction were also prepared, but by using PCC supplied by Imeris with different particle size and shapes. And the same aforementioned procedure was followed in these cases. The rheological characterization under shear flow was developed in a controlled stress rotational rheometer, the Andenbar MCR301, using a serrated parallel plate geometry with 10 mm of diameter and a solvent trap. And 2 types of tests were performed, steady shear and oscillatory tests. The steady shear tests were the controlled shear rate type. The effect of the shape and size of the particles was evaluated by submitting all the PCC prepared samples to these tests, and several parameters and their influence in the reference sample viscosity curve were also evaluated, such as the gap influence, the effects of the concentration of PCC particles, the impact of the temperature, and the results of the particle sedimentation. The viscoelastic properties of the reference sample only, the sigma Aldrich PCC with 55% mass fraction, were evaluated by means of large amplitude oscillatory shear tests, or LAOs, within the shear thickening range in order to understand the nonlinear viscoelastic behavior of the fluid. So in this slide, the reference sample viscosity curve is presented. This curve was obtained using the accelerated parallel plate geometry with a diameter of 10 millimeters and at a 0.75 millimeter gap and at 20 degrees Celsius. And as expected, the sample displays clear shear thickening behavior between the shear rates of 0.1 per second and 3 per second. The maximum viscosity value overruns the 1000 Pascal second, a decade over the viscosity value with the sample at rest. And afterwards, the shear thickening region, the sample exhibits a shear thinning behavior, which is common in these kinds of substances. To evaluate the influence of the geometry gap, several ones were used to obtain the shear viscosity curve for the reference sample. It is visible that by reducing the gap between the plates, the viscosity curve moves to the right and downwards, meaning the maximum viscosity is decreasing and reached at longer shear rates. The reason for this difference is the reason for this is explained by several factors, such as effects of non-parallelism, non-concentricity, and non-flatness of the cross-hatched plates, as well as the gap dependence measurements produced by uncarefully trimming the surplus of material around the plates. And the graph shows that for a gap of equal or higher than 0.75 millimeters, the viscosity curve doesn't show significant changes, which means that the gap independency was achieved. To investigate the effect of the concentration of the PCC particles, the aforementioned diluted samples were tested, and the shear thickening behavior is visible for both the reference sample as well as the 50% mass fraction sample. However, the difference between the maximum viscosity values of these two concentrations is clear, with a decrease of about 5 times from the 55% sample to the 50% one. To study the effect of the temperature on the viscosity of the shear thickening fluid, 5 tests at 5 different temperatures were carried out with the reference sample. The obtained results are accordingly to the expected. The increase in the temperature causes a decrease in the viscosity throughout the deformation profile. And it is also visible that the viscosity curve slides to the right with the increasing temperature, meaning the maximum and minimum viscosity values are achieved at higher shear rates. To study the effect of particle sedimentation, a sample was taken from the prepared reference sample and was left in the container for 30 days. At the end of this time, material was removed from the upper part of the sample and submitted to rotational shear tests. At the end, the same sample was left to rest again, and after another 30 days, the process was repeated, and so on for the remaining days. After 30 days, the effect of sedimentation is already noticeable, with the maximum viscosity value decreasing about 4 times its original value. And after this period, no more relevant changes are exhibited, at least until 120 days. Afterwards, there is visible decrease in the values of the viscosity when it reaches day 180. And it is also interesting to notice that the ratio between the maximum and minimum values of viscosity appears constant throughout time. In order to perceive the influence of the shape and size of the particles, 3 kinds of PCC samples were prepared. They were all supplied by Imerish and had a concentration of 55% like the reference sample. They were submitted to steady-state rotational tests with a 10 millimeter parallel plate geometry a gap of 0.75 millimeters and at 20 degrees Celsius. And the obtained shear viscosity curves are shown in the slide, as well as the reference sample one. And as you can see, none of the SOCAL samples behaves like the reference sample. The SOCAL 312 doesn't even exhibit shear thickening behavior. Instead, its viscosity is a typical power law. And the other two SOCAL samples, the P2 and the 31, show a slight shear thickening region, although the maximum viscosity achieved doesn't even surpass the 100 Pascal second, which is 10 times lower than the reference sample's peak viscosity value. In order to understand the nonlinear viscoelastic behavior of the reference sample, Laus tests were conducted, and they basically consist of amplitude sweeps that reach strains higher than the limit of the linear viscoelastic region. In this region, case is around 1.6% in strain. We intend to get information about the shear-induced microstructure within the shear thickening response. The sweeps were performed at two frequencies, 1 radian per second and 10 radians per second, and the graph shows the moduli results obtained for the Laus tests. The shear thickening region is visible, as well as the progression towards shear thinning behavior at high strains, which was the behavior expected regarding the shear viscosity curve results. It is common to present the stress response through a function of both the strain and the shear rate, and these kinds of plots are called Lissajous curves and are shown in the next slide for the 7 selected strains. In this slide, the Lissajous curves of the material are presented. In the left ones, the ones obtained at the frequency of 1 radian per second, and at the right, the ones for 10 radians per second. If the sample would behave as a perfect solid, the plots would look like a straight line passing by the origin of the reference system, being the slope of that line the shear modulus of the solid. And if the material would behave as a perfect liquid, the shape of the plot would be as a perfect circle centered in the origin of the plot. And as expected, none of the graph is neither a straight line nor a perfect circumference. All the curves exhibit a viscoelastic behavior, as expected for this material, which is a viscoelastic fluid. Nevertheless, it seems that for a frequency of 1 radian per second, the enclosed area is bigger, that allows one to affirm that is a quasi-viscous behavior that remains constant in a big range of deformations, meaning probably a stable structure. So after the shear rheological characterization, the extensional tests were carried out, submitting the reference sample to uniaxial extensional flow using the extensional rheometer caber. The silhouette of the filament thinning process was recorded with a high-speed camera equipped with the right optical setup to avoid optical errors. The experiment was run at different initial extension rates, corresponding to the shear rates in the shear thickening region of the shear viscosity curve. The time evolution of the filament thinning was recorded since the beginning of the experiment at 50 frames per second for the first initial extension rate and 125 frames per second for the remaining points. After the test, the set of images for each initial extension rate was post-processed using the software MATLAB in order to obtain the time evolution of the minimum diameter of the filaments. The filament profiles obtained for each initial extension rate, together with the pictures captured, reveal a typical viscoelastic behavior. It is even possible to witness the occurrence of beads on a string morphology for some initial extension rates, which is a typical phenomenon observed in polymer solutions under extensional flow. The evolution of the minimum diameter or radius in an extensional test displays a linear region in a semi-log graph, followed by an abrupt decrease in its value, evidencing the breakup of the filament. And in the linear region, the real-time extension rate is constant, and therefore can be calculated through the slope of the function as shown in the presented equation. This graph shows a comparison between both the shear viscosity curve and the relaxation times that were calculated for each initial extension rate. And it is quite interesting to observe that within the shear thickening region, the relaxation time follows the same trend as the viscosity. And even the maximum in the relaxation time occurs when the maximum viscosity is observed. And to sum up, with this work, it was possible to formulate an eco-friendly dispersion of PCC particles in a carrier fluid and understand how the different parameters tested impact its viscosity. The prepared fluid proved to be a shear thickening one, whose viscoelastic nature was confirmed by the oscillatory experiments and extensional rheometry. And the concordance between the results of both the shear and extensional rheometry is very interesting, and evidenced by the superposition of the viscosity curve and the relaxation times. So finally, I would like to acknowledge and thank FCT for the financial support, and finally, thank you for your attention.
Thank you very much, Miguel, for this really nice presentation. I will ask the audience for questions. There is any question in audience? Just let me see it in chat. There is any questions? I think not. Okay. I have a question. You call it in the title of your presentation that is a eco-friendly non-Brownian suspensions. Why you name it as a eco-friendly?
It is eco-friendly because we use carbonate calcium, which is abundant in nature and comes from limestone, and we don't use any polymer, for example, and glycerin, which is organic fluid.
As well as I know, these particles from the sigma, they are synthetic, not natural provenience.
They are precipitated from the stone.
Oh, okay. I think they are completely synthetic from.
Okay, I don't think so. But
okay, no, I was just curious.
I'm not sure about that.
Yeah, because sometimes the synthetic process for obtaining the particles are not so eco-friendly as you think they are, if they are synthetic, sure. Okay, thank you very much for this nice presentation. We're gonna move for the